Hello all. So welcome to this new lecture in this course on time series modeling and forecasting using R. So again in today's session what we will do is we will quickly revise a few properties about the time series process called as random walk. So from last session if you remember we kind of delved into multiple properties such as let us say finding the variance function or finding the ACF function or finding the auto covariances of some very basic time series models. For example, let us say autoregressive and then moving average, right. And then we specifically took some lower orders of these two models such as let us say AR1 or MA1 and then MA2, and we kind of established all these properties by working them using a pen and paper. And then towards the end of last session if you vaguely remember we talked about expanding a few more properties about the random walk. So in today's session we will quickly revise those properties about the random walk, and then in the later half of the section I will try to bring in some ideas about how to plot a time series, how to visualize a time series using R, alright. So initially if you again recall that this exactly is a random walk. So yt equals mu plus yt minus 1 plus et, and then again as always ETs are nothing but IID sequence of random errors with let us say mean 0 and then some fixed variance sigma square e. Okay. And above all this mu is nothing but the overall mean there, alright. So again, so if you notice this equation of a random walk, what I can do is I can keep on replacing these recursions, for example let us say yt minus 1 or let us say yt minus 2 and so on in a recursive manner to expand it further, right. For example, what would happen if you write down yt minus 1, so yt minus 1 would be nothing but so yt minus 1 would be nothing but let us say yt minus 1 equals mu plus yt minus 2 and so on and so forth, right. So wherever you have a subscript in the past, so let us say yt minus 1, that would be further expanded into yt minus 2 and so on and so forth. So this would be equal to mu plus let us say yt minus 2 plus e of t minus 1, right. And then the eventual next step would be to expand this yt minus 2 further and further and so on. So by recursion one can actually get a neat formula for this time series process yt, and which could be kind of summarized in this manner. So yt is what? So yt is nothing but t mu plus summation of all the error terms from 1 to t. Okay. So t mu plus summation ej and then j going from 1 to t. So this is an equivalent representation of a random walk, alright. So this is an equivalent representation of a random walk. So now what we will do is we will quickly look at some of the properties of this random walk. So for example, the expected value or the mean of the random walk happens to be t mu, right. Now again just for a second if you go back a slide, this would be kind of evident from this alternative structure, because if you take expectations on both the sides then what will you have? So if you take expectation of yt, this would be nothing but t mu plus 0, right, because expectations of all the errors are 0. Okay. And similarly if you take variances on both sides then what will you have? So on the left hand side you will have variance of yt, and t mu is a constant, so variance of any constant becomes 0, and then you will have a variance of summation ej. So then you can bring out the summation and then take the variance inside, right. So this would be something like variance of summation ej, which would be nothing but summation of variances of ej, and remember that each individual variances are equal to sigma square e, alright. So eventually this would be nothing but summation of sigma square e, and this is probably what exactly you have on the next slide. So variance of yt happens to be gamma 0, which is nothing but t into sigma square e, because how many terms are there in the summation? You have exactly t terms. Okay. And now the last important part is gamma k. So how would you write down gamma k for a random walk? So gamma k, if you remember from last lectures, is nothing but covariance between yt and yt minus k. Okay. So here I can replace yt, so this guy is yt and then this guy is nothing but yt minus k. Okay. So yt minus k here and then this is yt, and then the idea is to find out the covariance between yt and yt minus k. Now again remember the technique I told you in the last couple of lectures, that wherever you have common subscripts, those elements would add up to variances. For example, E1 and E1 or E2 and E2, right. So for that matter if you notice this carefully, So all these subscripts from E1, E2, E3 up to Et minus k occur in both the places, right. So eventually what will you have? So we'll have T minus k components of sigma square E, right, because exactly T minus k elements or T minus k subscripts are common between the first element in this covariance and the second sum in this covariance, right. So eventually the answer is nothing but T minus k into sigma square E, and all the remaining terms would be zeros because subscripts are not matching, right. Now again just one small disclaimer that subscripts are not matching, so the covariance happens to be 0, and why exactly? Because all the errors are independent, right. So for example, covariance between E1 and E2 or E1 and E3, wherever the subscripts are not matching, such covariances happen to be 0 basically. And now the last step is to find out rho k or the ACF function. So by the way, this is nothing but the ACF function of the random walk. So as per the formula, ACF is nothing but gamma k divided by under root of both the variances. So T minus k into sigma square E divided by under root of T sigma square E into T minus k into sigma square E, which sort of reduces to this function, okay. And exactly the last line kind of gives you that what could be a few examples where one can actually try to model a random walk. So for example, share prices or real exchange rates or GDP of a country and so on and so forth. So all these are kind of valid examples where one can actually try to model these data sets using a random walk. And now the last thing that we have is a few simulations. So here you see a few simulations of a random walk. So let's say on the left hand side we have a simulation where the overall mean mu is 0, and on the right hand side we have a situation where the overall mean is, let's say, 0.1. And immediately you can sense that both these situations are completely non-stationary, right. So in general a random walk is supposed to be non-stationary, and why exactly non-stationary? Because let's say the mean depends on t or variance depends on t. So we saw these properties earlier, right. So if you go back a slide, this is exactly what one can conclude from these two ideas. For example, the mean depends on t or the variance also depends on t. So if something is dependent on time, which is t, then the process can't be stationary, it has to be non-stationary, right. So I guess this kind of sums up a few important properties of really basic time series models. For example, let's say random walk or AR1 for that matter, or moving average with orders, let's say 1 or 2, right. And this sort of establishes a rather larger kind of a situation where you kind of analyze a few things or a few properties about all these basic ideas much more stronger, okay. Now if you remember, towards the end of last lecture I kind of gave you as to how can one identify models based on the ACF plots and PACF plots, right. And then we kind of stopped the last session there. So just to introduce this idea, and then we'll spend a few minutes here, and then kind of this idea is kind of important to us also, that how do you identify some very basic models using the ACF plots and PACF plots, okay. Now again, just to summarize this plot or this window or this slide, so what you have is you have the ACF plots of two different models in the first row, and then you have the PACF plots of two different models or the same models on the bottom row, right. Now the left column gives you AR2 and then the right column gives you MA2, okay. So autoregressive model of order 2 and then moving average model of order 2, right. Now just by seeing all these four plots here, one can actually see some special things going on. For example, if you observe this ACF for MA2, which is given here. So by the way, in each plot if you notice, you have horizontal blue lines. So these horizontal blue lines represent some hypothetical confidence bands, right. So if any spike is outside the bounds or outside these lines, we will say that that particular correlation, either ACF or PACF, is significant, okay. So possibly in this plot, the first correlation is significant, then the next one is significant, but after that all the correlations are not significant because all the spikes are in between the blue lines. What do you mean by this is, let's say if you number the lags. So the first spike is lag 1, second spike is lag 2, then lag 3 and so on, okay. So what this plot is telling us, so the ACF function of a MA2 process kind of cuts off after lag 2, and then this property is easily seen here, isn't it. So at lag 1 you have a significant spike, at lag 2 you also have a significant spike, but after lag 2 all the other spikes are not significant. So, we will say that the ACF function of a MA2 process cuts off after lag 2. Okay. And exactly similar thing is observed in this PACF plot for AR2. Can you see that? Right. So, the same thing is happening here. So, let us say if you again number the lags. So, this would be lag 1, then lag 2, then lag 3 and so on. So, what this plot is telling us, the bottom left plot, is that the PACF function for an auto-regressive model of a certain order, so let us say 2 here, cuts off after that order. Okay. So, one can actually get a cutting off tendency from either the ACF plot or PACF plot of either a AR model of a certain order or a MA model of a certain order, right. And you will see something special happening in these plots also. So, if you look at these plots, so the top left one and the bottom right one, what we can say is that these plots are, so you see a tailing off tendency. So, tailing off means what? So, tailing off means that something is kind of gradually decreasing, right. So, tailing off tendency in let us say this one, so this plot here and then the bottom right plot here. Okay. So, one can actually analyze all these 4 plots individually, or for that matter one can analyze an ACF plot and a PACF plot, and so as to somehow get an idea about a possible model that might be fitted on the data, right. So, if you want to expand this in general, right. So, what one can say? So, one can say that if the ACF plot, right. So, if the ACF plot for an MAQ process, if you are analyzing a ACF plot for a MAQ process, then it has a cutting off tendency. So, the plot cuts off. So, the plot cuts off after what lag? So, after lag Q, alright. So, if you want to identify an MAQ process using the ACF or PACF plots, then one has to specify or one has to focus on the ACF plot, and if he or she is seeing a cutting off tendency in the ACF plot, then we can actually say that the model could be, it is a high chance that the model could be MAQ. Right. Similarly, if you want to identify a particular AR model of a certain order P, then one has to focus on the PACF plot, and an exactly similar structure can be seen here, right. So, again just to remember or summarize this slide is that identifying AR model could be done easily using a PACF plot, while identifying an MA model could be done using ACF plot, right. And just one last line to kind of leave you at this is that if you are trying to analyze any practical time series data, and at an initial level you want to find out that what model could be best suited for the practical data, then one has to plot both these and then check. For example, ACF plot and the PACF plot and the tendencies and the behaviors within those plots to kind of possibly suggest a good model for the underlying data. Okay. Alright, so now what we will do is I will shift attention to a practical worksheet in R, and then we will try to kind of introduce some time series packages in R, and then try to work with some practical data and then see that how do you plot it, right, and then how do you analyze some trends in the data and so on and so forth. Alright. Okay, so here what we have is we have a worksheet in front of us which is called as let us say code 1, alright, and then if you look at the first line. So, for solving this worksheet or for going through this worksheet, we will be requiring one package in R, and then this package is kind of inbuilt in R. So, the name is T series. Now, again remember probably we covered this in the first session also, but then if not I will tell you once more that one can actually install any packages by going to this tools tab. So, if you see this tools tab and then install packages, and then here one can actually type the name of the package, for example T series, right, and then click on this T series and then click on install. So, it will install the package, right, and then once you install the package successfully, then you have to call the package in the R environment also, alright. So, that thing can be done using a library command. So, once you install the package, you have to call the package in the R environment by using library, okay. So, this is exactly what we will do. So, library T series, and you have two ways of running any line in an R code. So, one can actually click on this run here, which is the easiest one, or one can press control enter, right. So, control and enter. Okay. So, for this example we will be using a particular worksheet which gives you the US population data. So, if you see here on line 9, so this is exactly how one can actually read the data in the R environment. So, I am giving the data set a name, let us say US pop, And then what exactly is my US pop? So US pop is nothing but read.table because my data is in a text file. Alright. So since my data is in a text file, I will be reading the data from the text file. So read.table and then uspop.txt. Okay. So once you run this line, so by the way, all that you are doing in the R coding window here would appear in the console window. So the bottom left window is nothing but the console window. Okay. So whatever outputs you create or whatever commands you process in the coding window would be kind of outputted in the console window. Okay. And then again, one good thing is to observe that if you don't see any errors here, which means that the code has run successfully. Okay. So for example, as of now we managed to load the T series package in R, and then also we managed to kind of read the US population data which was stored in a text file into R successfully. Alright. Now again you have two things. So I think we discussed in the last lecture also that one can actually specify header equal to true or header equal to false. Now what do you mean by this? So again let me just show you the data, right. So if you type in US pop here, then this is exactly the data set that we have. So basically these numbers kind of give you the US population on a yearly basis. So initially the population was that number, then the next year the population grew to that number, and finally the last data point is exactly that. Alright. So this is my data set, and then how many elements are there? So you have 21 elements, right. So the length of the data or the sample size is nothing but 21. Okay. Now again here, like I mentioned, you have two things. So one can actually specify header equal to false or header equal to true. Now what do you mean by header? So for example, if you look at this data set, so the name of all the columns or the first row of any data set is nothing but the header. So header gives you kind of names of all the columns that are there in the data set. Okay. So if you specify header equal to true, it will basically, so R would treat the first row as the column names and not the data itself, right. I mean, so what might happen is that if you specify header equal to false, then this V1 that you see here might be treated as a data element by R. We do not want that, right, because V1 is what? So V1 is not a data point for us. So V1 is a column name for us, right. So if you want to specify and if you want to tell R that R should read the first row in terms of column names, then it's always a good idea to kind of specify header equal to true in that case. Alright. So for example here, right, if you again rerun this, so let's say US pop and then read.table US population.text while header equal to true, then again it will kind of process the same data that we saw earlier, which is by the way given here, but then now R will consider the first row as the column name or the column heading. Okay. So you have a small comment here that by default header equal to false is used, but what would happen if you kind of use header equal to true, right. And then one can actually use a scan function. So scan function is an alternative thing to kind of read any text file. So let's say scan and then US population.text. So one can use either or. So one can use read.table or the scan function. Alright. So let me run this, right. And then so again immediately in the console you see that the R has read 21 items. So it's a good sign. Right. Now the next thing is how would you be able to plot the data. So let's say if you want a very basic plot of the data set. So here we'll use a plot function. So plot function is again an inbuilt function. So one can use plot function on any given data set. So just for an easy idea or easy visualization, so what we are doing here is that we are kind of dividing each value of the population by that number, so that my y axis is not very elongated. So I want to compress my y axis, alright. And then these are some of the other technicalities that one should take care of inside the plot function. For example, type equals O. So type equals O means it will kind of output O's instead of straight lines, okay. And then main. So main is if you want to give a plot a heading. So in our case we are giving this heading to the plot. So US population from 1970 to 1990, okay. And then down the line you have X lab and Y lab. So X lab stands for the X axis label and then Y lab stands for Y axis label. So let's say X axis in our case is years, right, and then Y axis is nothing but the actual population in millions, right. And then last command is LWD. So LWD stands for length or the width of the pointer, right. So LWD stands for the width of the pointer. So how big or how small do you want all the pointers to be? So LWD in our case is 2 basically. And here you can kind of change the numbers here. So let's say LWD could be 1 or 3 or 4, etc. Okay. So now we'll try to plot this. So if you try to plot this basically, so again, so one can click on run here. And by the way, on this bottom right corner, so you see all the outputs which are either plots or charts, and so on and so forth. So this is a very raw plot, and one can actually zoom the plot. So if you zoom the plot, this would be the actual plot. Now let me extend this slightly. All right. So this is the plot that we kind of constructed now, right. So if you see on the x-axis, you have all the years like this, and on the y-axis, you see the population values, and this is exactly how the plot looks like, right. Now again, we have a small problem here that one can't find out that what all these pointers mean as far as the x-axis is concerned, right. So for that, what we can do is we can specify the x-axis. So I can specify my axis to be something like this. So I want a sequence from 1 to 21, and then starting from 1970. So the first point is 1970, or the first year is 1970, and then the last year is 1990. Okay. So if you add this axis command on the plot, now if you see the plot again, it will kind of give you the exact same plot, but then now we have the axis numbering there on the x-axis, right, something like that. Okay. Now let me try to zoom this slightly. Yeah. So now if you see that the x-axis contains all the years for us, and then you have a heading for the plot also, which says US population from 1970 to 1990, and so on and so forth. Okay. Now just couple of observations just by looking at this plot is that the graph of the time series is not stationary. So this example is not stationary because you have a clear trend, right. Okay. So let me close this graph and then move on. Now if somebody wants, he or she can actually save the plot or save the graph as a PDF file, and one has this inbuilt command which is called as PDF, and then you basically write down the name of the PDF file you want. So something like file equals uspop.pdf, and then if you run this, then R would automatically save a PDF version of this plot that you got here in the same working directory. Okay, in the same working directory. So again, I can run the same commands. So let's say plot, and then axis, and so on and so forth. Okay. Now the next idea is we will kind of try to play around with this generated plot. So let's say we'll try a transformation, because as we mentioned that this US population time series is not stationary, right. So how do you make it stationary basically, right. So how do you make it stationary? So one idea is to apply some transformation. So let's say square root transformation, right. So this root.uspop command is taking a simple square root transformation of all the population values. Okay. Now let's see that what happens if you replot this. So if you replot the same thing, then I'll kind of get a slightly different plot along with the axis, of course. Now let me zoom in. Okay. So this plot is nothing but it gives you the square root version of the same plot. So if you notice the y-axis, so things have not changed drastically. The only thing that has changed is the y-axis has become slightly different now, right. So the moment you take a square root, so it kind of compresses the entire plot even further. All right. Okay. So now since you've discussed that the plot is not stationary, so one can actually fit a linear line, right, because so just by looking at this plot, if you remember vaguely the shape of the plot, so I can actually fit a regression line or a straight line on all the points, because here you don't have a very severe curvature kind of a thing, right. So remember one thing, if the trend is looking more like a straight line trend, then one can actually fit a straight line or a regression line on that to capture the trend, right. So this is exactly what we'll do. So for that we require how many data points you have. So R has this inbuilt command called as length. So length of any data would give you the number of data points you have. So here if you input, let's say NT, so NT would output 21 because we have 21 observations in the data set, right. And now the next line is kind of fitting a very simple linear model or a linear line on that example. So again we will make use of an inbuilt command called as LM. So LM stands for linear model. Now here what exactly is the response variable? So response variable is my population data, and then my independent variable is nothing but 1 to 21, right. And then I'm giving a name to this command, which is fit. So if you run this, then it will basically fit a regression line on the population data. And from this I can actually run a command called as summary. So summary of fit, which would kind of give me a detailed output of the regression fit. So something like this. So let me elongate this further. So here you see that what were my residuals, right. For example, how are the residuals distributed, or how exactly are the coefficients kind of coming out. So for example, what are my regression estimates, and what are the standard errors, right, and what are the corresponding p values. So here if you see, the predictor is kind of very strongly try to estimate the response, because p value is significant, right. So p value is so small that I can actually reject the null hypothesis and then conclude that you have a relationship between my independent variable and the population values, okay. And down the line it gives you some other values also, for example r square. So here you see that r square value is very strong, so almost 1, right. So 0.9921 and so on. So these are some of the ideas that a summary command on the regression fit kind of gives you. Now what we can do is we can actually fit a straight line on the plot. So AB line and then fit. So if you run this AB line and then fit, now let me zoom in, okay. So what this AB line applied on the fit would give you is that along with the plot it will kind of give you a straight line fitted on the plot. So let me rerun this first. So let's say NT and then my fit command, right, and then if you want an AB line on that fit, then it should actually output a straight line on that fit basically, okay. Now the next thing what we will do is we will try to remove this trend, because we do not want the trend, right. So how can we remove the trend? So one can actually remove the trend by basically doing something like y minus y hat, right, where y is the actual value and then y hat is the fitted value, right. So y minus y hat is expected to be somewhat stationary, right, because once you subtract the fitted values from the actual values, one should actually expect that the resultant should be somewhat kind of a random process and stationary, right. So this is exactly our approach here. So let's say so the actual population value minus the fitted values, and then if you run this, then now if you want to replot this, so how would the plot look like? So my plot would look like something like that, where you don't have a trend basically. So it will be more like a stationary kind of a process, right. Or what I will do is, just for the sake of it, I will delete this plot and then I will try to replot a few things, okay. Yeah, so by the way this is the plot. So let's say so this plot kind of gives you the y minus y hat values. So once you subtract the fitted values from the actual values, my plot kind of looks like that. So here you see that the plot is not as non-stationary as it was earlier, right. So now you do not have a overall trend or something like that. So this is the idea. So one can actually try to fit a regression line and then find the fitted values, and then if you try to plot y minus y hat kind of a structure, then it should kind of resemble a stationary process, right. And once you arrive at this, then one can actually find out multiple things of that resultant, right. For example, mean. So in our case mean is close to 0 if you see, or the variance. So variance is 0.15, or the standard deviation, and so on and so forth, right. Now if you want, I can actually add a straight line at the mean to my plot also. So probably something like that. So just to tell you exactly as to where the mean lies basically, right. So once you plot y minus y hat, then my mean is so close to 0 that you have a horizontal red line at 0, right. So I guess these are a few things that one can do, I mean start doing by once you get hold of some practical data. So the first thing is to plot the data, then identify whether the data has some non-stationary structure or not. So maybe apply some transformation, right. And then maybe try to plot the complete data along with the x-axis labels, y-axis labels, a suitable title for the plot, and so on. And then depending on how strong the trend is, right, one can actually try to fit a regression line. So if the trend is not that strong, so if you have a straight line trend, then why not just try to fit a straight line regression and then kind of get hold of the fitted values, which are y hat, and then eventually or subsequently subtract y minus y hat and then get hold of a stationary process. Okay. All right, thank you.